Welcome to Healthcare Data Matters. Today, we will be talking with subject matter experts about perioperative autoregulation collaboration, the path forward to precision medicine. My name is Rajan Patel, and I will be your host for this session. Before we begin, we have some disclosures around funding and the operation of Healthcare Data Matters. These disclosures can be viewed here. Today, we have with us a group of esteemed colleagues from the University of Alabama at Birmingham, including Dr. Dan Berkowitz, Dr. Ryan Godwin, and Dr. Ryan Melvin. It is great to have you three with us today. Our session format is as follows. I'll ask you questions that give you the chance to present your work to our audience. Audience members can type any questions they may have in the Q&A tab as shown on this slide. At the end of the session, we'll address as many questions as we have time for. Does that sound good?
Indeed.
All right, let's dive right in. Dr. Berkowitz, can you tell us a little bit about the clinical problem you're trying to solve and why it has traditionally been so challenging?
Yes, absolutely, Raj. What we faced in clinical medicine has been the need to collect data in a time series dependent fashion in order to utilize it for both prediction and precision management of our patients. We talk about medicine, we talk about the importance of the ability to actually utilize data and information from our patients without the ability to actually collect it in real time and to utilize it to manage our patients. What we now have is the opportunity to collect high resolution data, analyze that data in real time, and utilize it to manage patients in a predictive and in a precision-based fashion.
That's very interesting. Can you talk a little bit about why getting that data is a challenging problem?
So as we look at the multiple ways in which or the multiple strata of information that is available to us, what our focus is on not the proteome, the metabolome, and all of the other ohms that really are important in defining our being, but rather the integration of that into what we would call the physiome, which ultimately is what drives our organ and integrated function. In the context of the operating room and in critical care, the ability to integrate devices has been a challenge for physicians and for critical care physicians particularly, because we have so many disparate, and actually you can see in the photograph above, we have so many disparate devices that need to be integrated, and each of them is their own black box. And what is important for us is not necessarily to have information isolated from each of those black boxes, but to look at the relationship between the data from each of those black boxes and to try and make sense of that in a more integrated fashion. And so what SickBay, MIC, and our data analysts have been able to really provide for us is a way in which we can time align all of this information, in which we can then observe subtle changes in waveforms and also look at the relationship between each of those waveforms and extract certain new physiologic information from that. And so this really is shown in my slide over here, in which we have all of these disparate devices. They're integrated in this black box. We have some algorithmic magic, and out comes new information that we can use to actually manage our patients in a precision and a predictive way.
I really liked your use of the word physiome, right? It sounds a bit like genome, right? Can you talk a bit more about, what that word sort of means and what, how you separate it into this idea of all these phys signals?
Yeah. So, we're a little bit obsessed with omics, okay? And as is demonstrated by this this figure on the left-hand side, which is really being has been popularized by Eric Topol's book on deep medicine. We live in a really remarkable era in which we have so much information at different depths and levels on our patients, on all of our patients. And as I said, that relates to not only our genome, because the genome really is the blueprint. It's not only how that genome is controlled, which is ultimately the transcriptome, and then ultimately the proteome, which is the proteins. And then integrated into the proteome is how all of those proteins are involved in the metabolic processes that happen. And then they're also regulated by epigenetic changes by the environment. So we have we have environment, and then the microbiome, which is all the organisms that live within us, which interact with our bodies. So what we look at when we look at the physiome is really the end result, the end result of the impact of all of those things on function. So when we talk about physiome, we talk about function. And really that's ultimately what we're really are fundamentally involved in and are interested in. We're interested in integrative organ function, because that's what we do as critical care physicians, and that's what we do as anesthesiologists. We sustain organ functioning during times of critical stress. We sustain organ function in times of critical illness. That is our job. So that's what I mean by the physio.
Yeah, that's a great word. I really like it. When I'm thinking about all these monitoring devices on the right, they're all measuring different signals over different systems. And as you said, right, it's the integration of all of these, these factors that determine organ function. And so in some level, being able to integrate these signals is going to be key to determining that sort of organ function. Can you talk a little bit about that integration? Like what's the, are there challenges there? What are the, going from that, many monitors in that room to sort of one stream?
Well, I think the challenge which MIC and sickbay has overcome has been this challenge of how do we get rid of multiple boxes, and how do we actually digitize this information in a way that is not just single box related, but is taking analog signals, digitizing them across multiple platforms. And so, again, this slide exemplifies what we used to do in the old days, when we were interested in integrating or in collecting and analyzing physiologic information. We would digitize it, and we'd have cots, and we'd run around into operating rooms. We'd put cots in those operating rooms, connect the back of machines and get analog signals, and then digitize them with AD conversion systems. and then analyze those data, analyze that data, usually not in real time, but sometimes in real time, and then often after the fact to give us more sophisticated physiologic information that we were interested in studying. The difference now is that we can do this across many different devices, and look at the relationship between those data sets, and as I said, extract new information. And so, for example, really interestingly, if you could even go back to the previous slide, we have been doing. There was one. Oh, sorry, I apologize. The top right-hand side. No, go forward. Sorry, I apologize. Go forward. Yes. So if you look at the top right-hand slide, that is a cardiopulmonary bypass machine, and that provides sustained circulation and oxygenation during times of intraoperative cardiac surgery, in which the heart is isolated from the rest of the circulation. And so we have recently been discussing projects that involved understanding and modifying oxygen delivery to patients, and optimizing that oxygen delivery so as to reduce potential organ injury and thereby reduce poor outcomes in our patients, whether they're renal or neurologic outcomes. And the only way we can do that is by extracting that information, all of this huge amount of data which needs to be integrated, and that data may be flow, it may be hemoglobin concentration, oxygen saturation, and that all needs to be algorithmically come together. We don't need just one of those measures, we need many of those measures together to calculate new physiologic parameters such as oxygen delivery, and then we need those parameters to calculate oxygen consumption and thereby look at the relationship between those two in near real time or in real time. The other example, sorry, go ahead.
Oh no, please finish your thought.
So the other example in which we've been working is in the area of looking at the relationship between blood pressure and blood flow in the brain. And that is regulated by a phenomenon which is well known in physiology called autoregulation. And autoregulation really defines the idea that that flow over a certain range of blood pressure is not, and that makes a lot of sense because we know that as our blood pressure changes, we don't necessarily have changes in our cerebral blood flow or in our consciousness. You know, if our blood pressure goes, but there are critical limits, okay, of that physiologic phenomenon. We know that because there are always limits. There are gains and limits to any physiologic adaptive mechanism. There have to be limits. And so when we're in a state where we're looking at complex physiologic changes, and when we're looking at complex surgical procedures where blood pressure, flows, etc., are changing all the time in fairly dramatic ways, we need to be able to understand what the limits of those parameters are, of those adaptive parameters are. And this is one of those examples. So if we go ahead.
Yeah, absolutely. And we're going to talk about those projects in a bit more detail in a second. One of the things that has struck me is the idea of bringing these parameters together to decide the best course of action for a patient. You've also chatted a bit about bringing people together, right? And drawing upon collaborations to bring these algorithms to bear on larger and larger groups. Can you talk a little bit about that? And then I want to hear more about the projects.
Yeah, sure. So, so you, yes, the critical importance of teams in this endeavor is irrefutable. I mean, we really need different skill sets. We need people who understand the complexity of surgical procedures. We need people who understand complex physiology. Most importantly, we need people who can actually understand and integrate in a way the data that is coming out of it, the data scientists, and they are absolutely critical to that process. So there's this this team approach, which is going to be critical, and really which is really something that is burgeoning, and which we're very proud to have. I would say the majority of those pieces here at UAB, and I know a lot of in other places have that and also having the IT infrastructure to not only analyze the data, but also to collect the data and to create the infrastructure to actually be able to create that data, I think is really just as important. So I think this is a team sport, and I think we need everyone on board.
Absolutely.
We need the dreamers, we need the physicians, and we need the data scientists and the IT integrators. So
absolutely. And I think later on we'll hear from Dr. Melvin and Dr. Godwin about that piece of the data science on the projects that you're all working on together, which is an exciting illustration of the exact idea I think that you're saying. So let's set some of that up. You've mentioned cerebral auto.
Raj, sorry, can you just repeat that, because I lost, I dropped it.
No worries. Yeah, so I think you're exactly right? It's the team that's going to make this happen. And oh, can you hear me okay?
Yes, I'm good.
All right. It's the team that's going to make this happen. And I think one of the things I'm excited about is you've started mentioning some of these clinical problems that you have seen. And I was hoping you could get into details on some of them. Vascular stiffness, I think blood pressure management, you'd mentioned autoregulation. Could you talk to some of those?
Yes, sure. And you know, this is just the beginning, and we're the beauty of sort of collaborative interactions is hopefully the fertility and the fertilization and the cross-fertilization that'll come, and the projects that'll actually emerge from that, and both cross-institutional, within the institution, etc. And so we look forward to that. This is one project that you'll hear a little bit more about from Ryan Godwin. We know that the stiffness of the arteries, okay, which really are predictors of vascular health, are really important as potential predictors of cardiovascular outcomes, both stroke, renal disease, etc., in the general population. This has not been as well studied or well defined in the perioperative space and in the perioperative environment. And so one of our projects, which we thought would enable us to utilize this high resolution data and look at, again, the relationship between the signals, the high resolution signals, would be to actually measure the velocity at which the pulse wave travels through the circulation in real time. And so what we're able to do is to, using our high resolution blood pressure signals and our EKG signals, determine the velocity at which the pulse travels, and we can use that as a surrogate measure of the stiffness of the arteries, and look at the relationship between stiffness and blood pressure, and the slope of the stiffness versus the blood pressure as a surrogate of vascular health. And so we can use that to determine and predict whether we can actually determine, or we can predict and determine whether stiffness has an impact on those outcomes that we talked about. So that's one small idea, it's one small project. I know it's turned into a bigger project than we might have predicted at first, and that's sort of the learning curve of doing some of the work. There's and that's the importance of having all of the skill sets, because often we can think up the ideas, but the actual execution is more complex than we might predict. So and so we can all learn something along the way from that. So that's the one example.
All right. I think there's a couple more if you're willing to indulge us.
Sure, absolutely. So if we can go on to the next sort of slide, we can go on to the next slide, because this just further goes into a little bit more detail about how we're actually measuring this relationship. And I think that Dr. Godwin will give you some more insights into that. So we can move on to the next. This addresses the issue of optimizing blood pressure, and we talked a little bit about the idea of autoregulation. So blood pressure, we know, is really a pretty poor surrogate of what we are really interested in understanding in the context of organ perfusion, organ oxygenation. Unfortunately, we use that because it's the only thing we have, or it's one of the things we have that's easily measurable, okay? And it's been measured for the last 130 years, or however long it has been. But there is ample epidemiologic data that suggests that if your blood pressure is below a certain threshold, the chances of you undergoing an event, renal dysfunction, or a stroke goes up significantly, particularly if the blood pressure is sustained at a lower level for a significant period of time. Now, we know that this, again, is a composite of data from hundreds of thousands of patients. And while that's really important from an epidemiologic standpoint, and we can make assumptions and decisions based on that, we know that information really does not help us to manage patients in a precision manner, individually and independently. We know that patients, this composite includes and encompasses patients that may be 20 and absolutely healthy, and patients that are in heart failure, have hypertension, diabetes, and are old. And we know from just pure physiology that those two are not the same animal at all. And so what we're more interested in is understanding whether we can determine the limits, the lower limits of blood pressure, as I said, of that physiologic adaptive response. What is the lower limit of that adaptive response in each individual patient? So if we can go on to the next slide. Now, again, this is the classic cerebral autoregulation curve that we've talked about, in which if we plot on the y-axis blood pressure and cerebral blood flow, and on the x-axis mean arterial pressure, there is a window. We are classically taught a window between 60 millimeters of mercury and 160 millimeters of mercury, and that's changed depending on the books, in which the flow, the cerebral blood flow, is independent of mean arterial pressure. And as I said, that might be the composite information that we have, but that doesn't tell the story for each individual patient. And so investigators over the last 10 years have been able to look at the relationship between cerebral blood flow and mean arterial pressure by measuring both of those variables, plotting them in real time, and then looking at the, I think we can go into the next, if we can hit the slide. I don't know if it, does it change? And then, yes, and looking at in real time, the correlation coefficient between those variables. And you can see that if the correlation coefficient is close to 0, we can make an assumption that the relationship between blood pressure and blood flow is independent. On the other hand, if the correlation coefficient between those variables, and you can hit the button again, Raj, is 1 or closer to 1, then we can say that they are absolutely linearly correlated, okay? And if on the right-hand side, as you can see, if we plot those two variables, i.e. the correlation coefficient, HVX, and we can go into the details of, go into the details about what that is, we plot those in real time, we get a very nice, what we call a cerebral autoregulation curve. If we use the cutoff point of not 0, but if we use the cutoff point of about 0.3 as the very low correlation, then we can see that the lower level of or the lower threshold of autoregulation in this particular case, which is a real case, is around 60 millimeters of mercury. So it's consistent with, you know, I guess all this composite data. And our optimal blood pressure is where the correlation coefficient is 0, and it's going to be closer to 75, 77 millimeters of mercury. And so again, this just emphasizes the importance of creating new information from streams of data that we can time align, we can process in real or near real time, and in that way gain more insight into and manage our patients in a more precision-based fashion.
Those are really, really interesting projects. And that's a good key takeaway, I think. Are there any others that you would want the audience to know about before we transition to Dr. Melvin?
So I don't have any other projects, but I want to say the advantage, while these kinds of physiologic phenomena have been studied, what is really critically important is the ability of sickbay MIC and these integrating systems and data acquisition and analytic systems is to do this at scale. So instead of having this done in one patient at a time, we can do this in as many patients as we have hooked up to the devices and hooked up to the systems. And so again, take home device integration is key to success, right? You need the right team, access to the data to rapid support, and that enables us to do predictive and precision analytics at the scale, which is what we said, which is key. And teams, we need collective intelligence and interinstitutional collaboration to realize the benefits of all of this analytics, AI, in order for us to have patient-centered and patient-centered care. So
thank you for that great background and into the clinical problems that are being solved. Let's shift our attention to the rest of the team, because as you said, it's a team effort, right? The clinicians, the data scientists working together to solve these clinical problems through data. So Doctors Melvin and Dr. Godwin, Dr. Melvin, can you tell us a little bit about working with the data to get these clinical insights? Have you had to do it before? What are you doing now? And sort of what is the difference in the impact as a data scientist?
Absolutely. I think there's sort of a cycle that's been the standard of practice for medical research. And that's that if you want to go find something out, go collect data, go investigate a project, like say renal autoregulation, which is just, are your kidneys getting appropriate oxygen because of your blood pressure? So if you wanted to research that, you might have to go to your favorite vendor and say, dear vendor, do you please have a device that measures this one particular thing that I'm after? And then hopefully they do, and you buy it, you spend a lot of money. And then if it doesn't do exactly what you want, you're often just sort of out of luck because you had no control over the creation of that box that you bought. And you're probably not doing a big enough project to really move them toward making a change just for you. And let's say something goes wrong, you're always reliant on that manufacturer, on that vendor for help. And even if it's successful, the next time you want to do a project, you go and buy a different device that's specific to that project and not reusable. So that's sort of the old paradigm, wheeling in a cart with a laptop and the monitors that you wanted, like Dr. Berkowitz described, and you probably bought that monitor special. But now, because of advances in technology and ways of collecting new data, there's sort of a new paradigm that we can move to. And that's if you have some way of collecting signals, and that could be as simple as your electronic health record. It could be a specific product for real-time data collection in your ORs, ICUs, general care floors, wherever. But as long as you've got a data source, you can work with your data science team to put together a software package that does exactly what you want. And this is what we did, example, for cerebral and renal autoregulation. We used in particular sickbay to collect our signals at the point of the OR. So basically anything that's on a patient monitor, instead of that getting lost or a nurse having to write it down every 5 minutes, that's just automatically and passively collected with no change in standard of practice. So this is very easy to get this kind of thing approved. And we collect that data at point of care all of the time passively. It's just happening in the background. And so when someone wants to research renal autoregulation, for example, they come to us. We work with, in this case, the team at MIC, find papers describing this algorithm, put it together in Python, and then we can make adjustments along the way. There were lots of things we discovered that other people in the literature said worked that didn't work for us. Lots of little gotchas where we had to filter our data, but we were in control of that entire pipeline because we built the software in collaboration with MIC that would do this. And so now whenever someone wants to make a slight change to this or do something a little bit different, they just come talk to the data science team and we revise it for what they want to do. We're not spending thousands of dollars every time we want to do each individual project. This is writing code. So the iterative cycle is much faster and much cheaper, and we control all of it.
Can you talk a little bit? Oh, yeah, sorry.
Probably anticipating your next question. It's not just a concept. We've actually done it. I think we've got a couple of examples here. So we've done cerebral and renal autoregulation. We have a paper that appeared in British Journal of Anesthesia. And it does at scale for multiple patients retrospectively what previously you would have to do prospectively. You would have to plan to wheel in the laptop, wheel in the particular monitors, hook them to the patient. And that's obviously going to require enhanced IRB review because you're doing something that changes the point of care. But with this, all of these signals being collected in the background, it was a simple IRB waiver to get this project approved and to do it. And we were able to do it in bulk for patients that we've had come through our OR since we installed the sickbay system. And so this was fantastic. Someone had an idea, we tried it retrospectively. And I think the amazing part is we could do it for lots of patients all at once, retrospectively, without someone having to decide way back before these patients visited the hospital that we wanted to do it. And if you're curious about that project, that QR code there will take you right to the paper.
For sure, right? And so it's that idea exactly of the aggregate statistics don't necessarily tell you the whole story. And it's hard to get individual statistics that'll give you that patient-centered care because it's hard to collect them all at once, right? And so this is kind of, in a little bit, getting the best of both of those sorts of worlds. Dr. Godwin, we haven't gotten a chance to chat with you too much yet. Could you chat a little bit about some of the projects that have caught your attention in this space?
Yeah, happy to. As Dr. Berkowitz mentioned, the vascular stiffness has a lot of clinical relevance, and there's a lot of important information you can glean by having a real-time surrogate for that. And the question then becomes, well, how can we get to that? And as you see in this plot here, in the orange signal is the ECG. The green X's mark the algorithmically found peaks. On the blue signal, you'll see the blood pressure trace coming off the arterial sensor. And the black dotted line there indicates the algorithmically determined arrival of that pulse. So the time difference that was on Dr. Berkowitz's slide in kind of the theoretical sense is shown here in a real patient, during operation, and we can actually calculate all of those little delta T's. And as the patient undergoes surgery and maybe some of the physiome might change, we can get assessments of how that signal, the vascular stiffness, might be changing accordingly. So this is in still a retrospective phase, but again, since sickbay has been installed, we're able to pull those data right from the database and perfect our algorithm, really get it up to speed and get it to where it needs to be to perform in a real-time way. And as Dr. Melvin mentioned, there's a lot of little subtleties in the data. This is a nice snippet of clean data. Unfortunately, that's not how data always works out. And so a lot of what Dr. Melvin and I do is to understand where it's going wrong, what's happening, what is physically causing that signal. Is it something we need to figure out how to work with, or is it something that we can discard? And those are the decisions that the data science team has to discuss and filter out a lot. But yeah, that's a project that we're working on. It's going quite well.
Really interesting. And similar to Dr. Berkowitz and similar to Dr. Melvin, you've talked a lot about the team and working together. Can you give me a little bit more, like, could you talk about your thoughts around internal collaborations, like how to, what it takes, right, to get these projects accomplished? Yeah,
absolutely. It does really require a village. This is a sort of workflow diagram that some folks have put together in the anesthesia department, and it really kind of describes at a fairly high level all of the pieces that need to be in place for execution of a successful research project. And it's a lot of things. You need a mentor, you need clinical champions, folks who really understand where the pain points are clinically, what are the data points that are most useful, what are the data points that we can do things with. So we need some guidance on the clinical side. Then we need to do all of our due diligence and make sure that it's a novel work. That's part of research, making sure that it's novel, getting your IRBs in place, getting your study design well set up. All of these things require a lot of folks, and a lot of really smart folks who are dedicated and have a lot of developed skills that are nuanced and not a lot of folks have. And so you can kind of see from clinicians to faculty, librarians, IRB folks, data scientists, IT support. It really does require a group effort, and this is one of the ways that we've sort of drafted up how to approach putting a research project together, and really helps you see how many folks need to be involved.
It's really encouraging to see how y'all have solved this problem within your team, right? Of getting these kinds of clinical problems solved using data, right? Understanding all the pieces involved, all of the stakeholders, getting them together, getting them to agree and executing on these projects. I would like to chat a little bit. My understanding, Dr. Melvin, is that you want to zoom out from this a little bit and create a community of collaboration and collective intelligence to build upon these successful internal collaborations. Could you tell us a little bit more about your plans in this area?
Absolutely. The goal is to have a somewhat casual user group for folks that are working on machine learning and AI in the perioperative space, with a focus on high resolution data capture, particularly through sickbay, though I don't think we have to necessarily limit to that. I think this will look like all of us coming together and talking about projects that each other are working on, offering advice, saying, hey, we're working on that too, or we're working on something similar. Can we combine what we're doing and suddenly have a multi-center project that's much more likely to get grants? I just think that there is an opportunity as we start to move AI into the perioperative space to really build a big team of pioneers instead of just a few islands working on perhaps the same thing and not knowing that we could be pooling that effort. And so we have some ideas around structure, but I think at the end of this, there's going to be a survey that will help clarify that, because we really want this to be something that is audience and participant driven. We don't see this as something where just the four of us are coming together and always talking about what we're doing. What we envision is sort of cycles of presentations. What are you working on? Cycles of advice. What would you like to work on, but maybe don't know how to get started? And again, we're going to have a survey at the end that will hopefully clarify exactly what everybody would really want to get out of that. Because again, we don't want it to be a top-down thing where we're deciding, well, this is what we would want, and so we'll make a user group like that. For example, do we want to just have like a chat, something where we are occasionally dropping thoughts and questions and responding to each other? Or do we want to have like an email listserv or a very formal, like, no, we'll only talk once a quarter? You know, we're interested in what other folks who are doing perioperative AI want to do. And that's, again, because there's a real opportunity here. I think we've seen our radiology colleagues really take advantage of AI and in many ways make their jobs and lives easier. And so having seen that happen organically to the field of radiology, maybe we can do it a little more intentionally in perioperative medicine if we all get together and talk about how we want to use this technology.
Yeah, I'd like to echo Dr. Melvin's sentiments. I think the audience would agree with me, hopefully, that the team at UAB is doing really great work. And this session is about paving that pathway to enable more collaboration, the development of this collective intelligence. And so, as Dr. Melvin said, there is going to be a survey at the end of this session to figure out what the interests of the attendees are in terms of getting this user group together and what that might look like. The next session might be closer to a meeting than a webinar. As Dr. Melvin said, it might be a listserv, it might be something, a chat window that folks can drop in on. But hopefully today we can start that conversation. And start discussing clinical problems, the ways different institutions are trying to solve those problems, and how collectively these research groups, these clinical groups, can improve upon the science. I think it's an exciting idea, and I'm looking forward to seeing those in whatever form that communication ends up being. I think it's going to be very fruitful. We are going to talk about the survey in a little bit more detail when we wrap up. I think right now we're going to have a little bit of a Q&A session. We have a few questions from the audience in the chat. If you would like to add yours, here are the instructions on how to do so. So the Q&A box is open. There are a couple of questions that I can start with, actually, if you'll indulge me. The first, Dr. Godwin, you'd mentioned stakeholder groups for doing, internal collaborations. What are the key groups you would say, or this is to the whole panel really, that need to be involved to start a project like this, right? Like, what are the top, 2 or 3 groups to start getting into the room to chat?
Sure, I'd be happy to start, and if someone else wants to fill in the gaps, that'd be great. But if you go back a slide, I think that, or 2 slides, yeah, perfect. This sort of, that inner wheel, I think, kind of outlines the essentials, right? You have to have someone with a clinical vision who really understands the problems that physicians are facing in the perioperative space. what are the pain points, and what are the places where combining different data can bring about some new information that they can use. So got to have that. Without that, none of this happens, I think. And then data scientists, as we alluded to, the data is never perfect. There's how do you build the models? What are the different AI approaches to solving this? Maybe you don't need an AI approach. It's a buzzword. A lot of folks really just want to jump on the bandwagon. Sometimes good old statistics go a really long way. And so you need folks who can kind of interpret what is needed and understand the best course of action there. And that's where the data scientists are really essential. And I think in a lot of places I've seen data scientists also do what we're lucky enough to have help from our IT folks with the extraction, the transform, the loading of data, access to the EHR. I mean, there's just a team of MacGyvers at UAB who just do awesome work to really support Dr. Melvin and myself, so we can really focus on model building, getting really accurate, high quality data, and not worry so much about SQL queries, for example. So that's a really foundational resource of tremendous help. And then of course, you got to have the cogs that keep it all moving with financial and administrative support. So that's kind of what I think the main groups are, but it really takes a lot of specialized skill sets.
Thank you. All right. There's a specific question in the chat that going into the algorithm itself, what kind of filtering did you do for cerebral autoregulation before making the parabolic fit? This is an exciting question. It sounds like folks are already getting into it.
Sure.
I'm going to answer
that.
Guys, sorry, Ryan. I think I'm going to answer that. I'm just kidding. Just kidding.
So I'd also typed out an answer just in case. So I'll say it and then send it. We filtered out non-physiological blood pressure values, which I would have to double check, but I think the limits were 20 to 300 millimeters mercury. Basically, we would see a lot of times where they're putting in the line, or they're removing the line, or like something went wonky with the monitor, and you just have like long lines of values that didn't make any sense. And so those kinds of things do happen in the real world data. So we did filter out the non-physiological values. And then we actually have multiple channels of arterial blood pressure being recorded. And so we would pick the one that had the fewest null values after doing that filtering, which is a little bit of a subtlety. So we first do the filtering and then say, okay, well, which one of these, after doing that, removing all of the non-physiological values, has the most valid data in it. I think there's also like a little bit of a dirty secret that we're getting those values after the monitor's pre-processing. So there is a slight black box element to the filtering there as well, if we're being completely honest about it.
Thank you. This might be a good question for you, Dr. B. The framework seems a lot more general than periop medicine. Is there a specific reason to start there, or a plan to form a maybe more general user group? You know, you and the rest of the team are parts of multiple departments over at UAB, right? So the example that was given was perioperative and post-trauma may be interested in autoregulation or heart rate variability.
Yeah, I mean, it's a good question. In fact, you know, we have deployed our systems in the neurointensive care unit, and with regard to autoregulation, there are many questions that would be potentially useful in, you know, in the neurointensive care unit, whether it was surgery, perioperative stroke, perioperative subarachnoid hemorrhage. I mean, there's a multitude of different, I think the reason why we initially started in the cardiac operating room is just the richness of the data sources. So that's the only reason. But having said that, the impact might be greater elsewhere. You know, we've also started to think about, I mean, another project that we were very interested in is in the maternal fetal unit and looking at the relationship between signals from mothers and integrating signals with mothers and fetuses. Now, that has been done to some degree, but I don't think it has been done with the intensity and the fidelity that has been done, that can be done going forward. So we're looking at that. So we're certainly not we're not in any way restrictive. We don't think it should be restrictive. It's just where our domains of interest, the domains of interest that we control. And anesthesia is everywhere in many ways because we're in intensive cares all over the show. But no, we are that this should not be restricted to the perioperative.
All right, thank you for that. Yeah, so it's starting in one place, but it could branch out to many others. So speaking of branching out, another question: if I have my own data sets, what are the options for collaborating in the user group?
We've actually had some practice with this. We have worked with another researcher who was collecting data through a different system than we were, and he sent us an anonymized example set. And so from that, we actually adapted the code we had written for one of our projects where we were collecting data specifically through sickbay to data he collected through another vendor system. And we showed that it worked. So I think there's all kinds of opportunities.
Very good. Yeah, I think the easier it is to join a group and do useful work, right? The better it'll be for all involved, right? The more robust the analytics, the more broadly applicable, and then, you know, and I think ultimately it'll be the work will be stronger for it, I think. All right, so we are coming to the end of our time today. I would like to thank again the UAB team for joining us and sharing all of this great information. And I'd like to thank the audience for joining us today and participating. A replay of this webinar will be available on healthcaredatamatters.com and a podcast version on our Healthcare Data Matters podcast channel. While on the site, you can also check out our previous webinars and join the conversation on our associated social media channels. Now, as we close this session, you'll see a survey about the AI user group that the UAB team was referring to. We would really appreciate you staying for one more minute or so to complete it. It'll help inform the content for upcoming sessions for the group. And we will also be in touch with information on our next Healthcare Data Matters webinar and the perioperative AI user group meetings. So please stay on for a minute and fill out that survey and join the user group. Thanks again for joining us here today. At Healthcare Data Matters, we are grateful to have the opportunity to advance a new standard of patient-centered, data-driven care. Thank you, everyone. Have a great rest of your day.